All right, we're getting really close to the end. Here we're at Chapter 11, Section 7. Chapter 11, Section 7 deals with cones, and then we're going to do a little bit of work with spheres, and we are pretty much done with our material for geometry, which is just fantastic. So let's talk a little bit about cones today. Now, cones pretty much work the same way as pyramids do. A cone is technically not a pyramid because pyramids have to have polygons as bases, and a circle is not a polygon. But pretty much the formulas work all the same way. Just like cylinders and prisms were essentially the same, it's just that cylinders technically aren't prisms because of that circle base. So we're going to get some neat stuff. But one thing we did not talk about with prisms at all, or pyramids at all, was surface area. And we are going to talk about that with a cone. Now, in order to talk about surface area, we need to talk about something called the slant height. The slant height is not the same as the height of the cone. The height of the cone is inside the cone, or it could be outside if it's an oblique cone, and forms a right angle with the radius and goes to the peak. It's the actual height of the cone. The slant height is the height on the surface of the cone, which is a constant in a cone. Okay? All the way around the cone, that's the same height. It's a little bit trickier. We didn't talk about this with pyramids. It is more tricky with pyramids because surface area of pyramids is something we really only do with pyramids that have regular polygons in base, because otherwise the slant height gets very confusing. But we aren't going to talk about that with pyramids now. We're talking about that, about cones. Now, bottom line is we always wind up with a right triangle. And guess what? We're solving right triangles again. I remember in the right triangle unit, I was telling you guys, hey, you better learn how to do right triangles. We're going to be dealing with right triangles all year long. Okay? I'm going to go ahead. That right triangle isn't exactly oriented the way I want. So let me do this and just draw one. Okay? So essentially we're always going to wind up with this right triangle that we need to solve. My right triangle is going to have the following dimensions: the height of the cone, the slant height of the cone, which we're going to signify with a cursive L for the slant height, and the radius of the cone. Okay? So the slant height is always the hypotenuse, which is kind of confusing because the H height is not the hypotenuse, but we got to deal with it. Okay? So if I set up my Pythagorean theorem, I always know that the radius squared plus the height squared equals the slant height squared. So we can use our Pythagorean theorem here. We could also use SOHCAHTOA if we were given, for example, one of these figures and an angle. Then we could have to use SOHCAHTOA to set things up. So this really is a great review section in the fact that we get to work with our right triangles again, and that's a pretty important skill to have. So let's take a look at how this works in actually finding area. Now, they give us specific formulas here. The surface area, I shouldn't probably skip this. The surface area, this is basically the base area. And this pi RL is what we call the lateral area. Okay? Pi times the radius times the slant height. Yeah, that's the lateral area. I guess that is a correct formula. The way I look at it, I'm sorry, I paused for a second there because the way I'm used to doing this is the lateral area for a pyramid is usually the perimeter of the base times the slant height divided by 2. That's the formula I'm used to using. Here the perimeter of the base is 2 times pi times the radius, because that's a circumference times the slant height divided by 2, and the 2's cancel out. That's why this formula works. So pi r squared plus pi rl. That is the formula for surface area. Notice it does not involve the height at all, except if we have to use the height as part of our calculation for the surface area, for the right triangle. We will use our height in the volume calculation, but we use our slant height in the surface area calculation. Something to keep straight. Here I give you the radius, I give you the slant height, there's nothing to solve, so it says find the surface area. We simply use our formula, pi r squared plus pi rl. My radius is 4, so that's pi times 4 squared plus pi times the radius times the slant height. That's 16 pi plus 24 pi equals 40 pi. And now we give a context. What units are we going to use? Well, it is an area, so we're going to use units squared, so inches squared. That's all there is to it. But what if I don't give you the slant height? What if I give you the height instead? Well, we're going to have to use Pythagorean theorem to find the slant height now, aren't we? So we're going to have to solve our right triangle. I mean, the surface area is still going to be pi r squared plus pi rl. I know the radius is 5, so this is going to be 25 pi, because 5 squared is 25, plus pi times 5 times we need to find that slant height. So setting up my Pythagorean theorem, 5 squared plus 12 squared equals slant height squared. 25 plus 144 is 169 equals slant height squared. So the slant height is the square root of 169. So the slant height is 13. And 5 times 13 is 65, so that's 25 pi plus 65 pi. And 25 and 65 is 90 pi, and in units, context. 90 pi centimeters squared, that is my surface area. Why is surface area important? Because if you are building a container in this shape, and you need to figure out how much material is needed to use to build that container, that is the surface area. And certainly everything we buy pretty much comes in a container that has to be designed by somebody. That's why we want to know surface area of a cone. All right, this one is for you. Now, I will give you this little bit of a note. Notice the radius is given as a decimal, so let's use 3.14 for pi here. Because, again, the context of the problem makes decimally approximating pi an appropriate choice. So this time you go ahead and you find the surface area. Now we need to talk about volume of the cone. Volume of the cone is the same as volume of a pyramid. It's base area times height divided by 3. In fact, even in the formula sheet here, it shows you that we're using exactly the same formula. Now we can't write a specific formula because the base area in a cone is always pi r squared because it's a circle. So I could rewrite it this way and maybe memorize a different formula, but I think it's easy enough to just remember that it's the same as a pyramid. It's base area times height divided by 3. Notice that I have a slant height on a right cone like this here. I've got my slant height here. On an oblique, however, things are a little difficult. I did not try to find surface area on an oblique, and I will not try to find surface area on an oblique, because you'll notice that the slant height is not constant. Because the center of the cone is not directly over the center of the base, the slant height is actually varying. And so finding that surface area is very complicated. For a right cone, we can do both. For an oblique, area volume is okay, but surface area is pretty much out for us. All right? So let's practice that. Here's an oblique. Find the volume of the cone. Because it's oblique, we can pretty much be sure they aren't going to be asking us for the surface area. Notice the values are decimalized, so we're going to go ahead and use our decimal values. The context of the problem tells us that decimal values are going to be okay. The volume is going to be base area times height divided by 3, like it is for any pyramid. Please don't forget to divide by 3. Okay? It's pointy. It's going to have less volume. If it wasn't pointy in a cylinder, it's just base area times height. It is pointy. It has a lot less volume. Divide by 3. Base area here is a circle, so that's pi times 2.2 squared times the height of 4.5 all over 3. So I'm going to take so I'm going to do 2.2 squared times 3.14 times 4.5 and divide that whole thing by 3, and I get 22.7964, 22.8 centimeters cubed. Pretty straightforward stuff, using the same formulas we've used before. Here's another oblique, and that's fine. Not hard to work with. This one, the context will use pi because we got whole number context, but it's the same formula. It's still base area times height divided by 3. My base area is pi times 7 squared times the height of 13 over 3. Well, 7 squared is 49. 49 times 13 is 637. So 637 pi over 3 inches cubed. And 637 over 3 does not reduce, so I will not try to reduce it. All right? So again, the context of the problem here is all whole numbers, nice, no decimals, nothing like that. So we can be precise. We don't need to approximate. We can give a nice exact answer like 637 pi over 3. I know a lot of you say that that's the 637 pi over 3. I call it a nice exact answer. I know a lot of you would argue and say, no, 22.8 is a much nicer answer because I know where that is. I'm not sure where 637 pi over 3 is on the number line. I'm not sure how that compares to other numbers. True, it is more complex in that sense, but it is also a lot more precise. It's not an approximation by any stretch. It is the exact volume of that shape. And that's the only way we can express it if we want to be exact. Taking it to 100 decimal places doesn't help because pi is an irrational number. All right, we've done that. One last problem for you. You get to find the volume of this, but it's going to be a little tricky because here it's a right cone, and notice 8 is not the height. 8 equals the slant height. 5 is the radius. I'm going to make it just a little bit easier here for you so we get nice whole numbers. I'm going to make this 13 meters. Okay, I'm going to change the conditions here and make that slant height 13 meters. So when you do solve for the height, which you're going to need for the volume, it'll be a nice whole number, and we can leave our answers in terms of pi. Okay? So I'm switching it up just a little bit, but you go ahead and find that, and that ends our notes for today.